we'll have a lot of these in the coming weeks. And if you don't know already, we'll actually have a lot of astroparticle speakers coming through over the next 2 weeks giving colloquia, so be sure to keep an eye out for when those are scheduled and show for those as well. But today we're extremely happy to have Alexis Brossard. Alexis completed his PhD here, but also at Paris-Saclay. And then began a postdoc here at Queen's University before now moving on to TRIUMF, where he's been working on cold neutrons, amongst other things. Today he's going to tell us about cold neutrons, and we're really happy to have him. Thank you very much.
Thank you. It's always a pleasure to be back home, first home. Okay, so as mentioned, yes. So today I'm going to talk to you about the ultra-cold neutron source, the TUCAN ultra-cold neutron source, which has been like designed and built at TRIUMF over the last several years. And on top of that, like today, I'm just gonna give you an update or a status, but like we produced our first ultra-cold neutron in June. So like it's really like a first ultra-cold neutron production talk, and I'm very happy to give this talk today. Okay, so to start, I'm gonna give you like a brief introduction of like not neutron, just ultra-cold neutron, and like what are ultra-cold neutrons and how we produce them and what can we do with them. So like what defines an ultra-cold neutron? It's like when a neutron is totally reflected on the surface at all angle of incidence. This is like the definition of ultra-cold neutron, totally reflected on surface at all angle of incidence. So it can happen if a neutron has a kinetic energy lower than the Fermi potential of the material making this surface. So you can see, like, I put you like some values of this Fermi potential. It ranges like around like 54 nano eV for aluminum. The highest Fermi potential is nickel 58 at 350 nano electron volt. So we talk really about like extremely low energy. And so like the common sense says that when we have neutron with an energy below 300 nano eV, can consider it's ultra cold, and then it's reflected on surface. The very nice things, because like they bounce on surface, is like we can like manipulate and store this neutron for a very long time. So the first things we can use, magnetic field. So the neutron has a magnetic dipole moment with this kind of potential. So like magnetic field will act as a barrier of potential. So basically, and like this potential is like roughly 60 nano eV per Tesla. So basically, if you have a neutron with 300 nano eV, a field of 5 Tesla, the neutron is going to bounce on the field. So we can store neutron using magnetic field. Finally, gravity. This is the potential of a neutron like in gravity, on Earth gravity. It's like 100 nano eV, roughly 100 nano eV per meter. So when you have an ultra-cold neutron with this energy, you can bounce on the floor, but it's going to go up 3 meters. So, and using these three things, strong force, magnetic field, and gravity, we can make everything we need, like pipe, valve, and bottles, to fill it with neutron, and store neutron in these things, which is quite amazing. Okay, how do we make this ultra-cold neutron? So I'm gonna describe like the TUCAN TRIUMF method, and I will give you quick information about other methods, but I will really focus on what we are doing. So first, we use a high energy proton. We shot this high energy proton on a high Z target. We have like an excited nucleus. It excites by emitting like gammas and particles, including neutron. So when we produce this neutron, like they are really far to be ultra cold. We talk about like hundreds of mega electron volt neutron. To obtain this first neutron, you can also use a nuclear reactor. This is what it's done, for example, at the ILL in Grenoble in France. And I think at Los Alamos, we have a UCN source based on reactor. Then we have this very high energy neutron. The first way to slow them down is just by elastic scattering. So this neutron, they will go through a material. Each time they bounce on the nucleus, they lose some energy. So we moderate them, we cool down the neutron using this like very like classical process of like collision elastic scattering. Finally, we go from this cold neutron, we convert them to ultra cold neutron through like super thermal production. It's like beautiful process. So basically, if we keep helium-4, at a very cold temperature, like around 1 Kelvin, this is a dispersion curve of this fluid. And like we see that if a free neutron has an energy of roughly 1 MeV, close to 1 MeV, it can excite the medium and emit a phonon in this medium. And then when the neutron does that, it really goes from like 1 MeV, like low energy, and it loses almost all its energy. And we end up to have like a few 10 for few hundred nano EV neutron. So this is how we produce ultra cold neutron from cold neutron. Other experiments use solid deuterium at very cold temperature. I won't talk much about that. Okay, so now you have roughly like an idea of the recipe. How do we do that at TRIUMF? First, we use like, this is like picture of like the TRIUMF facility. It has like a main cyclotron producing like 500 MeV proton beam. Wow, this proton beam is sent through like towards like a lot of different experiments. We are located like on this beamline. So we share the main beamline, the 1A beamline with several other experiments. This beamline, this is like a detail of our beamline. First, we have a kicker. So the kicker is used to kick the beam into our beamline regularly. There are like some like beamline tools, I would say, like bending magnet, quadrupole, several things, like some tools for diagnostic of the beamline close to the target. And this is what the target looks like. So it's a piece of tungsten. So you see like you have like a pen for scale. It's like roughly like this size, I would say. Obviously, it's placed in water because like this target can take a lot of heat. And so yeah, it's cooled down during operation, and it's linked to a target extraction system that will basically like put the target into a lead cylinder at the end of its life. Because like this kind of target at the end of its life, it's gonna be like kind of like maybe like 1 sievert per hour at a few meters from the target. So this target needs to be like very well shielded to be handled. So yeah, we send this high energy proton into tungsten. Then the moderation step. So this is like a drawing of the experiment. You see that the target is placed, like we have a volume of different material placed on top of the target. The first thing is like heavy water at room temperature. And then we have a layer of liquid deuterium enclosed inside this heavy water. And we have graphite all around to kind of reflect the neutron. So you see that we have a layer of graphite, layer of room temperature heavy water, and finally a layer of liquid deuterium, which is kept around like 20 Kelvin. The liquid deuterium is kept at this temperature by a LD2 liquid deuterium cryostat, which is a thermosiphon. And like here you can see like 2 MCNP simulation that shows the accumulation, that shows like where we can find thermal neutron, mainly into the room temperature heavy water, and where we can find cold neutron. So mainly inside the liquid deuterium. At the center, at the really center of this geometry, we have the production volume that contains isopure helium-4 at 1.1 Kelvin in the production volume. Just a little precision about isopure helium-4. So when you take like natural helium, like the helium you can find in all the helium cylinder on the first floor, it contains roughly a ppm of helium-3. It's already low, but like the absorption cross-section of helium-3 is such high that if we would use natural helium, like we would just like absorb all the neutron on the helium-3, we would not observe ultracold neutron. So we are isopure. It means that we have roughly 10 to minus 10 to 10 to minus 11 atoms of helium-3 per atoms of helium-4. So like really like extremely pure helium-4. Finally, so as I mentioned, so the cold neutron goes into this conversion volume. of isopure helium, helium-4. Then they become intracold. So they start to bounce on the walls because the walls are coated with nickel, like with good material. They start to bounce on the walls and like they diffuse. Basically, they diffuse like a gas towards the experimental area. This is quite challenging because like in this part, we have in the isopure helium and like in the walls of the conduction channel, we have roughly a heat input of 10 watts when the experiment is running, which is quite high. And also, you see, like, keeping isopure helium at 1.1 Kelvin, it's not very complicated. And I would say it's not very cold. If I compare to super CDMS, these kind of things, it's much, much colder. But like having this quantity to be kept at this temperature under like this heat load, it's quite challenging. How do we overcome this?
Just a very basic question. The deuterium, but the liquid and the heavy water, is this for creating neutrons, or what is the purpose of having those around?
Alors, the purpose of these two things is this stage.
It's that stage. So okay.
Going from high energy to thermal and to room temperature and cold neutron.
Okay,
and then when we have cold neutron around 1 MeV, these cold neutron are converted to UCN under like by phonon emission. Okay, and so yeah, to overcome this challenge, we have like this helium-free cryostat and this heat exchanger and this conduction channel, which are like all of them kind of like state-of-the-art, each of them. Like we have a state-of-the-art cryostat, which works extremely well, state-of-the-art heat exchanger and conduction channel. So first, like, just gonna give you some description of how it's made. So the production volume and conduction channel, it's like 6 layers of aluminum welded together. We have the liquid isopure helium, vacuum, vacuum, liquid deuterium, vacuum, vacuum. All of that is placed on top of the target, connected to the cryostat. So the first layer was designed like a while ago and tested at Los Alamos, at the UCN source of Los Alamos in 2020. And it was completed last year in 2024. This is the cryostat. You see, it's like a quite high cryostat. It's like more than two meters tall. So basically, very basically how it works, we have like a first volume, which is filled with liquid helium by the helium liquefier of the TRIUMF facility. Some of this helium flow in a second pot. We pump the saturated vapor pressure of this helium, goes down to 1.6 K. Finally, we have helium-free flowing a bit in all of that, filling the helium-free pot. We pump on this helium-free pot, and we keep it at 0.8 Kelvin. This helium-free pot is connected to the conduction channel and the isopure helium through a heat exchanger. And then, like, all of that has been tested and qualified over the last few years. This is like a view of the experiment where, like, you can see the cryostat here connected to this like quite big pumps. This is like basically for cryogenists in this room, like the performance and the characteristic of these pumps. And like the target is placed below the yellow block, under the yellow block you can see on the back. And basically like the beam line is along this wall under all these yellow blocks. And this is like the heat exchanger. So this heat exchanger was like designed and built by KEK in Japan. We work with KEK. So basically we have this volume of helium-free liquid. It enters at 1.6 Kelvin. We pumped out, cool down to 0.8 Kelvin. All of that is copper. And like the isopure helium is kept at the center of the heat exchanger. And so this is how it looks like in real life. It's like a big chunk of copper with the surface plated with the right material. The helium-free filling line, the helium-free pumping. Here it connects the tail section and goes toward the target. And on that side, it connects the experimental area. So just very quickly, like we, like in 2024, we performed some cryogenic tests. We observed that the helium-free cooling power behaved as expected. So this is like, this plot shows like the cooling power of the helium-free versus like the proton beam current. And so like the proton beam current is strongly related to the heat input to the system. And we see that it works as expected. We just have like a static heat load of 2 watts, which was like a bit higher than expected. But we can survive with that, no problem. Okay, one of the things is, it's one of the study which is very important for us, and we're gonna like do to understand our system in the coming years. Basically, like we don't know exactly how the temperature of the isopure helium is gonna behave along the conduction channel and along the volume of isopure. And this is basically some simulation and calculation of what this temperature could be. So here we have the coldest temperature at the heat exchanger, and here we are at the production volume. And you see that 2 models like HIPAC and Van Schimmer can give like quite close, but like different temperature profile. And one thing which is very important is like the UCN losses in the isopure helium is proportional to T to the 7. So a very tiny increase of the temperature can lead to no UCN. So this is why we have to keep all this system extremely cold. And yeah. Okay, just like a quick update, we tried to make some Ultracold neutron in November last year. Unfortunately, we didn't have a proper helium purifier at that time. So we tried to purify through a small nitrogen trap. We clogged the system in 1 minute. So it was like a kind of over for this year. And like now, like we received like in March, like the full size helium purifier, like which is like much bigger and much better. And so like this year in May, we managed to condense all of isopure helium into the experiment. So it's a good first step. Okay, so now June 2025. Can I remove? Sorry, like all my titles are hidden by these things.
Hit the 3 dots on the right. Should be able to click hide.
Thank you. Okay, this is the setup from like June this year. So, as you see, like we are not quite complete. The volume of helium, heavy water is not completed. We missed some heavy water on the top. We have no liquid deuterium. Alors, why? It's because like having like 150 liters of liquid deuterium into a system pose some like safety and hazard issue. We are working hard on that, and we're gonna soon have 150 liters of liquid deuterium. And we don't have all the isopure helium that we need. You can see like it was not totally filled, but like the production volume was full, and like the conduction channel had roughly like half of the isopure helium it can take. We did not send neutron outside of the shielding in the experimental area. We just put like a gate valve that open and close the source, and we put like a lithium-6 detector here. So this is like the first test we did like to characterize the experiment. Okay. All right, I know that there is a lot of detector people in this room, so I'm gonna make one slide about detector, just to describe the detector we are using. So basically, like these detectors are scintillator. And they are made like of 2 plates of glass. Basically, like the top plate is depleted in lithium-6, and the bottom plate is enriched in lithium-6. So basically, like the neutron can go through the first plate, being absorbed by the lithium-6 in the second plate, and it produces like a very clear like tritium decay by alpha and tritium. And like by pulse shape discrimination, so this detector has 9 channels, and like by doing this pulse shape discrimination, we can clearly isolate neutrons from the background. And the advantage of this kind of detector, because we want to produce a lot of neutrons, so we need to detect a lot of neutrons, is that they are really quite fast signal, and this kind of detector can have like a megahertz detection rate. Finally, Friday, June 13, the first UCN production. Okay, basically like this plot shows the total rate of the lithium-6 detector. So basically, if we take this whole box, is a gray curve. The black curve is the rate after pulse check discrimination where we isolate the neutron. And here you can see like the valve which separate the experiment to the detector, valve open, valve close, etc., etc. And this is, you can see here when the beam is on or off. We turn the beam on. We see a huge rate for both like the background and like the background and like the neutron after pulse shape discrimination. We stop the beam, we open the valve, and we see this count rate decreasing like that. We were very happy at that time. Then we did the same things, but we keep the valve closed, and we detected almost no neutron. So you see, like it's a quite long time length. It's like 120 seconds, and we saw for the first time like neutron diffusing through the guide and being detected over 120 seconds. And after, like we repeated that several times, and we confirmed that the source was working and was producing ultracold neutron. So we were very happy at that time. So I'm just gonna talk quickly about like the background that we observe. Okay, so this is like a typical signal observed when we open the valve or when the valve is kept closed. And you can see that after each radiation, we have this kind of long background decreasing. And this long background decreasing is basically aluminum-28. I mean, most of it, large part of it is aluminum-28. Because like what I showed you, like the cryostat, the box, the cryostat is sitting on it, and most of things are made of aluminum. So we activate aluminum, and this aluminum decay with a half-life of 2.2 minutes and emits a 1.8 MeV gamma. So like this background is like quite clearly identified. Okay. So now, this is the awesome result of this first campaign of measurement. This is like the cross, blue cross, orange square, and green circle. They are like the predicted number of ultracold neutron produced versus the beam current. So it's based on simulation, MCNP simulation, cross-section for UCN production, and PenTrack, which is a software for UCN transport. There is like some correction from the main simulation to take into account the fact that we have less heavy water, we have no deuterium. These two are two models based on the two models of temperature. And so the first things that we see is that we are some numbers which are kind of close to each other between like the simulation and the number we detected. But the awesome result is that from the simulation and our understanding of the temperature behavior of the isopure helium, we were expecting a saturation, kind of increase in the saturation. And clearly we do not in our experiment. And it is an awesome disagreement. Because like we thought that we would be limited by the temperature of the isopure helium. And remember, T to the 7, it's a huge dependency, T to the 7. And finally, not. So we have a plan for the coming year and next year to build a system to measure the temperature along the conduction channel inside the heat exchanger, inside the production volume. But clearly, we thought that this kind of method, this kind of experiment will be limited by the temperature of the isopure helium. And like our experiment, like the thermal conductivity or whatever is behaving better than expected, and we don't observe any saturation. And so it means that we can push the beam current, we can go to higher current, higher temperature, and produce more neutron than we would have think at the beginning. And like it's like really a great surprise, clearly. Also, like the kind of experiment we did during this first lifetime experiment, this first irradiation. So we did like some saturation measurement. And so like you can see that whatever the current of the proton beam, you can see that after like roughly 100 seconds, we saturate. And also like we did some storage lifetime into the source. Also basically like it's very simple to do this measurement. It's just that instead of opening the valve right away after the beam irradiation, you just put a delay and you count the number of neutrons after this delay. And we measure, depending on the condition, we measure a lifetime between 25 and 30 seconds. And first order, it's in good agreement with the simulation that has been done over the year to design the experiment. Okay, the NEDM experiment. I think I have time to go through all of it. So, okay. Okay, why do we want to measure the electric dipole moment of the neutron? So basically, it violates T symmetry. Electric dipole moment of a neutron violates T symmetry, and so CP symmetry. So it's a test for model entry beyond the standard model. Okay, so it can be done by using like the Ramsey precision frequency method, which I will briefly describe later. And ultracold neutrons are very suitable for this kind of experiment. So first, the Ramsey method. So basically, how does it work? We have a neutron with spin up, which is placed in a parallel magnetic field. And then we're gonna apply an oscillating B1 field. When we apply this field, the spin is gonna flip. Then we're gonna let the neutron spin like have a free precession for a given amount of time. And then we're gonna apply again this oscillatory things, which again was gonna make the spin flip down. So here, this plot shows like the probability of observing a spin up after doing a Ramsey cycle. And you see that it strongly depends on the B1 frequency. This plot is just an example, and it's not a real plot. But basically, by doing this experiment with 4 different fields, we can measure the resonance frequency of the neutron. So now, if we apply an electric field parallel to the B0 field, if we apply this electric field, and if the neutron has an electric dipole moment, during the free precession time, if the fields are parallel, it's gonna basically increase the precession, and if the fields are anti-parallel, it's gonna like reduce the precession. And so basically, like this same figure of like the probability of observing a spin up is gonna be like slightly shifted compared to having no electric field. And just go one side up. Just the thing is like we look for very, very slow shift. The resonance frequency is like 30 Hertz and 1 microtesla when we apply 1 microtesla. And here we talk about 20 nanohertz in the same condition if the neutron electric dipole moment at this value. So you see it's a very tiny shift compared to like the precession frequency. Okay, now I think one equation. This equation here show like the statistical uncertainty of this type of measurement. So basically, it's like inversely proportional to the visibility. So what we call the visibility is like keeping the spin of the neutron in the right direction. For example, if we send neutrons with spin up into the neutron guy, this alpha take into account basically how many neutrons will shift by bouncing on walls for whatever reason. Then it's inversely proportional to the electric field. You want to apply as high as possible electric field. This is why we need a great source, because n is inversely proportional to the square root of the number of neutrons detected. So obviously we need to produce as much neutron as possible, and like if we have a better neutron source, we're gonna have like better statistical uncertainty. And finally, this is why ultracold neutrons are very suitable for this type of experiment, because like this uncertainty is also inversely proportional to the free precession time. So remember, like we have spin up, we put them horizontal, and then they have a free precession time. And so as longer is this precession time, better is this uncertainty. And like basically, like this is why neutron that can be stored in volume, like in container, for like minutes or hundreds of seconds, can really like reduce this uncertainty. Okay, this is like the improvement of this limit. So far, electric dipole moment of the neutron has not been measured, but limit has been put with time and improving with time. So the base current limit is this one, roughly 10 to minus 26 ECM. And now many groups, so us, PSI in Switzerland, ILL in France, and some people in Los Alamos, and some people in Russia, China, and other experiments are in the goal of reaching like this limit. It's our current goal. Okay, so now I'm gonna describe, I'm gonna go through like some detail of the NADM experiment. So basically on all this side, keep in mind, it's like kind of like the same picture, but with the source. So the source feeds neutron. This ultracold neutron go through a supraconducting magnet and they are polarized. Polarized neutron through neutron guide. It's really plumbing, it's neutron plumbing. Through neutron guide and through valve goes into the precession chamber. In this precession chamber, we apply the magnetic field, the oscillatory field, the electric field for a given amount of time. Then this neutron exits the precession chamber and goes into a spin analyzer, like neutron detector and spin analyzer. On top of that, all of this experiment needs to be placed in an extremely quiet environment in terms of magnetic field. So this is why it's enclosed in this box, which is like a magnetically shielded room, and which contain like some coil to create the B field, and like some shielding to protect from like the magnetic perturbation around it. So yeah, now I'm gonna describe a bit each of these components. So this is a magnetically shielded room. So basically, it's made of 6 layers of metal, 5 layers of mu metal, and 1 layer of copper. As you can see, it's quite tall. It's several 10 meter tall. And basically, it allows to shield magnetic field by like few tenths of thousand. It has a reduction factor of few tenths of thousand, depending on the frequency of the field. And like this box was like completed last year and fully tested this year, and so it works within the expected range. Then we have like a coil, the AMC, ambient magnetic coil compensation. So it's placed around the box. The main purpose of this coil basically is to counteract the magnetic field of the cyclotron, because like it can be kind of weird, but basically like we need to have an extremely quiet magnetic environment, and we have no choice than to put this experience very close to this huge magnet, which is like the cyclotron. So this is like this ambient magnetic compensation is just a coil that is gonna like counteract the effect of the proximity of the cyclotron. Then we have some like the main field coil, which is placed so like inside the box and which is gonna create the magnetic field. Also, we have like some smaller shin coil, so it's basically like some square coil placed a bit everywhere inside the box. And this shin coil, they are here like are first to characterize, to do some like they will be here to do some like statistical systematic uncertainty test. So we're gonna induce a perturbation and see how the results behave. And then they can also be here to compensate some like magnetic field that could still go through, let's say, like through the shielding.
So are the coils to measure magnetic fields coming in anyway, or are they to like counteract them, or what are the coils exactly for?
Or they can counteract a field. This is like when we want to take data to do this measurement, and they can also be used like to induce a field and to test systematic uncertainty, basically. Okay, then we need to have like a very good measurement and knowledge of the magnetic field within like the precision chamber and around the experiment. So we are developing like mercury magnetometer. So basically, we're gonna have like a bit of mercury vapor inside the system and like measure magnetic field like that. We are developing an array of cesium magnetometer, which is gonna be placed a bit everywhere around the experiment, like just to make sure to measure if we have gradient across the experiment, like a gradient of magnetic field could induce like false signal. Finally, like this is a design of the storage cell as it's gonna be built and developed next year. So basically, like here we have the main electrode. And also we're gonna basically, if we have a magnetic field along the cell and we apply the electric field in between, we're gonna have like parallel electric magnetic on top and anti-parallel in the bottom. So we're gonna do like that. We can do like kind of both measurement at the same time. We also develop, obviously, like we developed this cell and we went for like some tests before we had our own neutron source. We went for some tests at J Park in Japan. And basically, like we were able to measure and to store neutron for this lifetime into this type of cell, like 132 seconds. So clearly, like we showed that we are capable of handling and storing neutron for a long period of time. And also, like obviously, like we need to have everything needs to be very quiet in terms of a magnetic field. So we did a lot of study of materials because basically any like, I don't know, like, you know, washer, bolts, everything that's gonna enter this room needs to be like non-magnetic. So we did an intensive study and to select material and get the best material as possible. We also developed like UCN guide, and like by applying like by putting the right magnetic field on this guide, we can like keep the spin of the neutron while we are going through the guide. It's the alpha parameter of the statistical uncertainty. So we want to keep the spin of the neutron in the right direction. And finally, like this is a spin analyzer. So basically, like how it's made, it's like it's a UCN detector. It's an ultracold neutron detector. And by applying or not a magnetic field, remember like the 60 nano eV per Tesla. So it's gonna completely block one spin polarity and let the other go. So this is like basically how it works. It's a detector with a magnetic field on top. So you see, like this experiment require a lot of development in shielding, neutron storage, neutron detection, magnetic field, etc. So this is the, okay, I'm almost done, great. This is like the top view of the experiment, like that shows a bit like all I've been talking about today. This is the cryo pit with the cryostat, the beamline is here. This is the pump pit with all this big pump that needs to be pumped on the cryostat. And here we have like the UCN guide that can feed guides in two directions. So basically here we're gonna have a first guide that's gonna feed neutron into the magnetically shielded box for the neutron EDM experiment. And we have a second guide which is gonna feed neutron into an experimental area. And this experimental area will be open for users. So if you have an idea of some things to do with ultracold neutron, and you want some ultracold neutron, please come and we will give you some ultracold neutron. Okay, what?
How much per?
We can talk about that. Okay, so to conclude this talk, almost on time. So the TUCAN collaboration, we produced our first ultracold neutron in June 2025. It's a very exciting result. Like we have like very promising results. This fact that we do not observe saturation of the number of neutrons by increasing the beam, it has to be understood. It has to be understood, but it's very promising for the future. It really means that we can do more current, bigger source, and yeah. And we need to do some like more cryogenic study to fully understand like the temperature of the isopure helium and the behavior of the whole system. It's gonna be done like we are doing it. The source will be fully commissioned by the end of the year. Like for the deuterium system, we are just missing a few signatures now, but like I'm confident that we have a beam time. We have another beam time by the end of September. I'm confident that we should be able like to fill the LD2 system and have like the complete source. And like the complete source, this is the yield we expect. Right now, we are just producing like a few percent of what the source, the file is designed to make. Then we're gonna build the NEDM experiment in 2026. So unfortunately, we are not gonna make UCN in 2026 because in 2026, TRIUMF undergoes a long shutdown for commissioning of other things and some repair of the accelerator. Like so, no neutron in 2026, which is nice somewhere because it's gonna give us time to finish and to complete the neutron EDM experiment. And like the neutron EDM experiment will be like fully commissioned and start data taking campaign in 2027. Yeah, and so yeah, we had one Queen student to produce this ultra-cold neutron. Thank you. Yes, sir.
So, ultracold neutrons are in vacuum when you're measuring them, or are they in pure helium form?
In vacuum. They are produced in pure helium-4. Let me find you a right picture. Okay, so basically the level of helium-4 will be, in the final design, will be up to here. And so after, like they are in vacuum in all this space. And below, under like the gate valve, all these parts are pumped with turbo pump, basically.
So you showed sensitivity, which is significantly better than 10 to the minus 27 than the existing measurements, but you also mentioned, or other experiments, that are pushing in a factor of 10. What about your sensitivity and schedule and so on compared to these other experiments?
Alors,
comparable to what's contained in the
that's the things, like we are preparing a neutron source which is gonna produce like much more ultra-cold neutron than the other experiment. I think there are another experiment which already is taking data for this goal of 10 to minus 27, but I think I don't have the number in the head, but I think it's like a factor 10 less neutron than us. So really like the main advantage of our experiment will be the source, because we're gonna have a neutron yield like one order of magnitude at least higher than other experiments.
Why do you expect the counts to saturate, or why did you expect the counts to saturate? Like,
for the reason, for the T temperature to the 7 dependency of the absorption of a phonon by a neutron. So when we have ultra-cold neutron, they can absorb a phonon and become non-ultra-cold. They gain energy, and at that time they are not reflected on the surface. They just.
I get that, but why, if they're moderated to the same degree, is it just because of the spread in the temperature that you expect to be wider in the hotter beam? Because I mean,
Yes. Basically, higher beam means higher heat, and higher beam, higher temperature, and higher temperature means more phonon reabsorption and loss of neutron.
So much by model of just more neutrons despite whatever that's wrong. It's because the beam is hotter, everything gets hotter.
Yeah. More beam means also because like we have like gamma flowing through the helium. We have like all kinds of particles like that will go through the helium and warm up the helium. Like it's really like a radiation warm up from the target.
Just annoying question about that graph, saturation.
you sure it's not saturated?
Yes, let me.
Because there's basically one data point, and it could be either.
That's the red
Oh, not the blue one.
Alors, no, like basically, like these two sets, black and red, they are just like two data sets with, it's just two tests that we did. You see here, there is a foil that separates the guide. It's like these two data sets are just with and without the foil. And this is the simulation, like no, I'm sorry, Aaron, it's a straight line. And like the simulation showed, I would say, like shows like a saturation, like tend to saturate where we still do not observe it. Obviously, all of that needs to be confirmed. We need to have the full source because like basically we scale the simulation by the fact we have no LD2 or we redo some simulation somewhere scaled. So yeah, we have to confirm that with the full source, with the deuterium. The only thing is like so far, we will not be able to go above 40 microamp because like our beamline is like designed for 40 microamp. We have the CNSC license at 40 microamp. So going higher in beam current, it will be possible, but it's not something you do very quickly. Like
Can you get a smaller resolution in beam current, like smaller step sizes? Is that possible?
I think, yeah. Oh yeah, we can. Okay, but you know.
Really confirm.
Okay, but you know what? Like I think.
Looking at that error bar, it could be on the line, it could be on the X.
Okay, so people from TUCAN online listen to.
Question a different way. You understand why the data points are so far below the simulation?
No. I mean, again, like the thing is, like this simulation probably have big error bar, which are not shown on this plot. It's like the scaling of this simulation, like put some error bar that are not shown, but like.
Can I ask a quick question that follows up on Art's question? So what would you say is the bottleneck to your EDM measurement? Is it actually the flux of neutrons, or is it how long they remain stable in your bottle, which you said your thing can give around 120 seconds with your current design, as opposed to the 20-30 seconds that you observed so far, or is it related to how precisely you're actually going to measure the spins and the final read out? Like, where do you is there a sense yet where the actual bottleneck is going to be in terms of it's really just neutron flux in the end, or is it?
Yeah, I don't know. No, the neutron flux will contribute. I think that's one thing that can limit us at some point is like the high voltage you can apply in the cell. So because like so far we did some tests and we are developing a cell. Basically, like we are managed, I think, to apply like 100 kilovolt in this volume. But it's like this is a limitation that we can improve, yeah, we have to characterize like still like the spin transportation and the spin analyzer. So I would say like the bottleneck can kind of be all of that at the same time.
I was actually going to say, you keep saying you scaled down the simulation. What do you mean by that? So
no, so but basically like we redo the MCNP simulation with less D2O and less isopure helium. Then in terms of like Bayesian production, so once you know like the population of like MEV neutron into the production volume, you can rescale the number of and you know the level of isopure helium, so you can rescale the number of ultra-cold neutron. And then like we did basically we did some simulation into like with the whole volume of isopure helium full. Here we have some things a bit different because like we have like kind of like liquid and vapor pressure on top, and so we did not redo this transport. This whole we're working on that right now and redoing these simulations with like not the full volume of liquid. So this is why, and I think this is why like we rescale a bit like to take into account the fact that we had less isopure helium for the transportation.
Right. That's the reason I asked. I wonder if something weird with the geometry is happening, just explaining
Yeah, alors, the things. Yeah, so again, like the thing that we have not simulated is like basically we should have liquid up to here. So it obviously it modified the geometry of the system and of like where like the ultracold neutrons are produced for sure.
Well, no, there's a question offline. Okay.
So someone asked, what is the speed of your neutrons?
The speed of the neutron, it's roughly like a walking human, a few meters per second.
Maybe a quick question from
Do you mind tell more detail on what happened with the purifier? What was the problem?
Okay. The problem we had some isopure helium. The isopure helium is stored in a big tank outside of the building. We had isopure helium from several sources, and you know, like we have like this big tank, probably outgassing like water, oxygen, air, whatever. We have long piping, which could not probably be properly cleaned, properly warmed up, which outgas, same thing, these kind of things. And then when we try to liquefy that, at the end or somewhere in the cryostat, it's very thin. It goes through needle valve with an opening, like very, very small opening. And we send some air or some water or some crap through this opening, kind of froze immediately. And then like you have ice of these things into the system, and the only way to get rid of it is just to warm up everything, pump everything out, and recool down and restart. And the purifier, basically like the purifier, it's like a two-stage purifier. One stage is at 70 Kelvin. It's charcoal, activated charcoal. One stage at 70 Kelvin, a second stage at 20 Kelvin, and we circulate the helium through these two stages, and then we send the helium to the cryostat to be liquefied and fill the volume. And like basically, like if you send dirty helium, well, you have like a needle valve somewhere here, and you have an ice cube.
Let's,
Thank you.